Good day. We're here again with another lecture for static of rigid bodies. So today our topic would be about the position vector. So we are still in chapter 2 and here are our objectives. So we've covered most of it from the previous lectures, and now our objective is to still express the force and position in Cartesian vector form. So now we will be dealing with the position vector and explain how to determine the vector's magnitude and direction. And the following topic would be about introducing dot product in order to use it to find angle between two vectors or the projection of one vector onto another. So let's define the position vector. So it is defined as a fixed vector which locates a point in space relative to another point. So let's discuss here shortly the classification of vectors. We have a free vector which is composed of magnitude and direction. So there's no particular line of action and point of application. You can transpose it as long as you don't change its magnitude and direction. You also have the sliding vector which has a magnitude, a direction, and a line of action. Okay, so you can slide it along this particular line of action. And then we have the fixed vector, has magnitude and direction and a particular point of application. So that this in this classification is where our position vector will fall. So let's take this example here. We have a Cartesian coordinate system here, an x, y, and z axis in the origin at O, and we have points A and points B. So we can define these 2 points by indicating it as a position vector. So as you can see from the origin, for point A, you need to go 4 meters along the positive x-axis, and then 2 meters along the positive y-axis, and then 6 meters along the negative z-axis. So this point will have the coordinates of 4, 2, negative 6. While point B here, we can locate point B by going this 4 and 2 meters. So going 6 meters along the positive x-axis, 1 meter along the negative y-axis, and then 4 meters along the positive z-axis. So this point B will have coordinates of 6, negative 1, 4. So recall that we are still operating on a right-handed coordinate system. I hope you remember that, where the positive x would be the direction of your fingers, positive y would be the direction of your arm, and positive z is the direction of your thumb. So if you are confused with that, kindly refer to our lecture 4 to review that or read it in our reference material. So now let's take the Cartesian vector form of our position vector. So if we have here a point P, which is denoted by x, y, z, we can write our position vector as r. Okay, so our position vector will be denoted by small letter r. So r is equal to xi plus yj plus zk. So that is the coordinates of the point. So you can still remember ijk, which denotes xyz components. So for a particular point with x, y, z, so this vector here r, from the origin, you will go x units in the x axis, y units in the y-axis and z units in the z-axis. So you have x comma y comma z, and you can write the Cartesian vector form of this particular position vector in this form. So now we have a position vector r, and we have points A and B denoted by their coordinates, which are x sub a, comma y sub a, comma z sub a for A, and x sub b, comma y sub b, comma z sub b for B. So for point A, we have the position vector r sub A. For point B, we have the position vector r sub B. And we have here a position vector r. So in this case, this position vector will be called RAB. Why? Because we will name our position vector from its origin point to the head. Okay, so in this case, for this blue position vector r, the tail is from point A and the head is in point B. So we call it RAB. So you can see here, some position vectors will have only a single letter in its subscript. So when you see something like that, it means that the tail is at the origin. Okay, so one subscript denotes that the position vector tail is from the origin. Two subscript denotes the point from A and 2. That's why RAB. Okay. So here, by head to tail vector addition, if you can still remember this triangle law from lecture 2. So this is a triangle, okay? So head to tail. So from the head of RA, so R sub A, to the tail of our vector R or RAB, then we can write RB as the vector sum of vector RA and R. Right? You can still remember that. You just connect the two vectors that you want to add from head to tail. So in this case, we have RA plus R, and that will equal RB. Or if we will transpose RA, we will have the equation for our vector RAB as equal to R sub B minus R sub A. And writing the respective Cartesian vector forms here, so R is equal to R sub B minus R sub A. That would just be equal to, so x sub bi plus y sub bj plus z sub bk minus x sub ai plus y sub aj plus z sub ak. So we can now write the Cartesian vector form of our vector R or RAB by finding the Cartesian vector form of both RB and RA and performing the vector operation. So if we will further simplify that equation, and we can do scalar operations on those in the same direction, right? So for those in the I direction, that is the x components, we can put them together. So we have x sub b minus x sub a I plus y sub b minus y sub aj plus z sub b minus z sub a k. Okay, so just remember, it's the head minus the tail. Okay, so if b is your head, that should be x sub b minus x sub a. Same goes for the y and z. If it's from b to a, that would reverse, of course. Just remember that it is from head minus tail. Okay, so if you have RAB, that would be b minus a. So this is another representation of that. We have point A and point B, and we have here the blue vector R. This is x sub B minus x sub A in the I direction, and so on for y, j, and zk. So just remember this equation, that this is still the same as saying xi plus yj plus zk, but here we have 2 points, the head and the tail, b minus a. Okay, so if the vector is reversed, let's say this arrowhead here is pointing at point A and B is the tail, this will also reverse. Okay, this would be A minus B. So now let's go directly to the force vector directed along a line. So if we have a chord AB, and when we can define it as a position vector if we know the lengths of it, right? We have point A and point B. And we also have a force directed along that line. So we can conclude that if we introduce a unit vector u, they will have the same unit vector since they are having the same direction. So we can use that to find the Cartesian vector form of the force. So we have a force directed along the chord AB. So remember, it should be directed along. That is having the same direction as that chord. So we have a position vector R denoting the chord AB. So RAB with the same direction and sense for the force. And we will be using the unit vector from the position vector. That would be U is equal to the vector R over the magnitude R. So that would just give you that would just give you the 1, a unit vector, okay, magnitude of 1, but with the direction that denotes the chord. And that direction will also denote the force. So what we can do here is we will multiply the magnitude of the force with the unit vector that we found from the position vector. So our u, which is just r vector over r magnitude multiplied by the magnitude of the force. So therefore, recalling the equation for a position vector, this long equation here, we can find it by the Cartesian vector form. This is basically the Cartesian vector form of that, all over the magnitude of that. So you just square each of the differences, xb minus xa, yb minus ya, zb minus za. And this would be the equation for your unit vector. And then you will multiply it with the force. Okay. So now let's take an example for us to better understand that. So we have our force vector. So the man here at point B pulls on the cord with the force of 70 pounds. So we know that the magnitude of the force, 70 pounds. So what we are to do is to represent this force acting on the support. So the support is point A here as a Cartesian vector and determine its direction. Okay, so here the dimensions are given. Point A is 30 feet from the origin, and point B has this coordinates as well. Okay, so let's try to apply what we have learned so far in order to solve this problem. So our approach for this problem is of course, we will be using the position vector and the unit vector that describes its direction, and we will apply it for the force with a given magnitude. So first, we will establish the r, a position vector from point A to B in Cartesian vector form. So we can do that since we have the dimensions. So from the components of r, we will find its magnitude. Okay, so we can, if we defined already the x comma y comma z coordinates of the position vector, we can find the magnitude of it. And then we will form the unit vector u, that would be the vector r divided by its magnitude, to find the direction angles and sense of both f and r. And then we will draw the Cartesian vector for the force with the origin at the tail of A and establish the direction cosines. Okay, so this would be our steps to solve this problem. So here we have the given right here. So when you are solving these kinds of problems, the diagram, this one, this would be your given. Okay, if you are able to draw this, that would be enough, and you will get the full points for that. Okay, so we have here, let me write down, we have the magnitude of the force given as 70 pounds, and we are required to express it in as a Cartesian vector. That is, we need the CVF of f. Okay, we need Cartesian vector form of f. Okay, so we described earlier how we will approach the problem. So here our solution. What is our first step? We need to establish the position vector. So what do we have here? We have an x, y, z coordinates. So we can find the Cartesian vector form for both point A and point B from the origin here, right? But what I want to do is, there are many ways to solve a problem, right? But what method we want to choose is the method where there will be fewer numbers, right? Okay, so for solving this problem, I will move my origin to point A. Is that alright? Okay, so my origin would be at point A. So point A now, since I assigned it as the origin, will have the coordinates 0, 0, 0. Okay, so since we want to find the position vector that would be head minus tail, it is easier because we will just be subtracting 0 for it. So for now, we need to find the coordinates of B with respect to our moved origin, which is in point A. Okay, so since point A is here, we can say that point B will have the coordinates in the x direction. That would be 12 feet, right? This is still the coordinates of B with respect to the origin A. So this is your x comma B. So we have 12 comma for the y. So the y coordinate is 8 feet. This is y B. But if we will follow our right-handed coordinate system, this would be in the negative y direction. That's why this would be negative 8. And z, since our origin is A and it's going down, will also be negative. And it would be, so from the original origin, point B is 6 feet above that. And point A is 30 feet above. So it means that with respect to A, B would be 30 minus 6 feet. That would be negative 24. So later I will also show you how to do it without moving the origin. I just want to first show you the easier way to do it. Okay, so that would be 12 comma negative 8 comma negative 24. So if we will find RAB, so let me write here our vector RAB. So from point A to point B, if you can still recall, that would be xb minus xa. So since all the coordinates of A is 0, since we designated it as the origin, RAB will just have, let's write it as 12. You have negative 8. You have negative 24. I JK. J and K. Okay, simple as that. Now, side note, let's determine let's define RAB when we didn't move the origin. Okay, so point A, I will just erase it later, but let me just show you. So point A would have the coordinates from this origin here. Point A would be 0 comma 0 comma positive 30, right? B would be from our original origin. For the x, that will still be 12. Comma negative 8, the same, comma 6 feet. So if you will do here the equation for RAB, that would be 12 minus 0. So you still have 12i. You have negative 8 minus 0. That will still be negative 8. You have 6 minus 30. That would be negative 24. So you have the same. You will have the same Cartesian vector form for your position vector even if you don't shift your origin. Okay. So for me, I just prefer to reduce the numbers. That's why we move the origin to A. Okay, so again, there are a lot of there are other ways, alternative ways to solve the problem, but of course you should go for the easiest approach so that you can also save time and you can minimize your errors since you'll be dealing with fewer numbers. Now that we have defined our RAB, we have to find its magnitude. So the magnitude R, so I hope you can distinguish between the magnitude and the direction here. I'm trying to write the vector as a boldface and the magnitude as just a default font. So this will just be equal to the sum of the squares of this 3. So that the sum of the squares, the square root of that. Alright, so we have 12 squared plus, that's negative 8 squared. That will give you a positive number, of course. Plus negative 24 squared, also a positive number. Let me just plug that in the calculator to find the magnitude. So if you follow, you can also do it on your calculators. That's square root of 784, and that is giving us 28. So it's a position vector, it's a measure of distance, and the units given here are feet. So that's the length from A to B is 28 feet, and this is the magnitude of our position vector. So our next step is to find the unit vector. So let's call the unit vector UAB. So UAB would just be equal to our vector RAB divided by, let me write that, all over its magnitude. And that would be equal to, we will just write this and divide it by 28. So we have here so we write that down as, we divide this Cartesian vector form with 28. So that's 12 over 28. That's negative 8 over 28. And negative 24 over 28. So this is 12 over 28. The common factor is 4. That would be 3 over 7. Let me write it down as 3 over 7. This is 8 over 28. The common factor is also 4. So we can write that down as this is again over 7. This is 2. This is 2. That's 8 divided by 4. And 28 divided by 4. That would be. So we're just simplifying fractions here. So we have here 24. That's divided by 4. That would be 6. So this would be 24 or 6 over 28 or 7. So we just simplify the fractions, okay? And we write here the unit vectors in each direction. That would be I, J, and K. So this is now the Cartesian vector form of our unit vector that we named as UAB. So why did we do this again? Because the position vector AB, if we take the unit vector describing it, which is UAB, sorry about that, okay, UAB, this is still the same unit vector that denotes the direction and sense of our force. That's why we take its Cartesian vector form, so that we can use it as to find the Cartesian vector form of our force, which is 70 pounds. Okay, so you can follow until now. So we will use this. So if you can imagine, the steps would be to find the Cartesian vector form of your position vector, find its magnitude in order to find RAB over RAB here, the vector over the magnitude, which in turn will give you the unit vector UAB, which will you use then to define the Cartesian vector form of our force. So here, let's write F, our vector F is just equal to its magnitude F and the unit vector UAB. And this is our UAB. So we can write it as we have 70 don't forget the unit since we are dealing now with the force. So our unit vector here is unitless. Okay, since this is RAB in feet divided by RAB in feet, so this is unitless. So if we multiply it with the force having this unit pounds, the resulting vector will also have the unit of pounds. So that's 70 multiplied by 3 over 7 for the x, 2 over 7 for the j, and 6 over 7. So I think you will not be needing your calculators here. You just need to multiply. You just need to divide everything by 7. That would be 10, and multiply everything. But if you want it to be faster and sure, not really faster, you can use your calculators. I don't know why it's not writing. I hope this responds. Okay, so here, this is 70 divided by 7, that's 10. So we can write our answer as, we have here 30. We have 70 divided by 7, that's negative, that's 10 times negative 2, that's negative 20. And divided by 7 times 6, that would be 42. And just write your I, J, and K. Okay, so I hope at this time you can follow the steps. So find the Cartesian form of the position vector, find the unit vector, and then just multiply it with the given magnitude for the force in order to find the Cartesian vector form of the force. And this is our answer now. 30I minus 20J minus 42K, that would be the Cartesian vector form of our force. We already know the magnitude of the force, right? Okay, so what remains is for us to find the coordinate direction angles in order for us to define fully the vector, since we need the magnitude, the direction, and the sense of the vectors. And we will do that with by doing what? Direction cosines. Oh, I'm sorry, this is actually not 42. This is 70 divided by 7, that's 10 times 6. This would be 60. Okay, I'm sorry. Let's write it down as 60. So you can check the magnitude should still equal 70. That's 30 squared plus negative 20 squared plus negative 60 squared. Take the square root of that. I won't write it here since we already have the magnitude. So what remains is to find the coordinate direction angles. So let me write it somewhere here on the sides just to save space. Okay, so for alpha angle, which is the x angle, that would be equal to the arc cosine of this, of the unit vector component, which is 3 over 7. And that would give us, if you plug that in, that's arc cosine of 3 over 7. That's approximately 64.62 degrees. So same for the beta angle. Beta would be equal to the arc cosine. Don't forget that you need to include the, so this angle would be more than 90 degrees since you know that it is negative, right? Of negative 2 over 7. So our cosine of negative 2 divided by 7. So it's more than 90, that is 106.6 degrees. And lastly, for the gamma angle, That is also more than 90 degrees since it's negative 6 over 7. That's arc cosine negative 6 over 7. And that gives you 148.99, let's say 149 degrees. So now you have your direction angles, you have the Cartesian vector form, you have expressed. So let me write here, this is our answer. You have expressed the force 70 pounds directed along the line AB as a Cartesian vector in Cartesian vector form. So this one, and including the angles. Okay, so we follow this approach to solve the problem, and this is our the drawing of the vector. So for the answer, you need to also draw the vector. Okay, so you have x, y, z coordinates, and this is your force 70 pounds with the unit vector u sub ab, and these are the angles are solved as, if we will go back in our whiteboard, these are your angles: 64.62 for alpha, 106.6 for beta, and 149 degrees for gamma. So for our final answer, please do not forget the units. So the force unit here would be pounds. So for our here, the position vector, the unit is feet. So always include the units. So another sample problem for a force vector directed along a line. So we have a roof, and it is supported by cables as shown. So each cable exerts force, so from force A to point B, that's 100 newtons, and from point A to C, force AC, that is 120 newtons. So it exerts 100 newtons and 120 newtons at the wall hook in A. So the task is to determine the resultant force acting at A. So we have two forces, we need to resolve it into a resultant force, and as well express it as a Cartesian vector. So again, we will use what we learned about utilizing the position vector to write the Cartesian vector form of these two, FAB and FAC. So here's our approach. So first, we form the resultant F sub R or FR by triangle law. So if you can recall, we can do, if we wish to find the resultant of FAB and FAC, we can do vector addition, and we can do that by head to tail addition. So if we put FAC here, this would be an equivalent length for FAC. We can form the parallelogram, and we can draw the resultant here as you can see, the one in blue. Okay. The next is to introduce the position vectors RAB and RAC. Since we want to write FAB as a Cartesian vector, we need to establish the position vector RAB. same goes for force AC. We need to introduce the position vector RAC. Okay, so we will be looking for two position vectors. So first, we draw what the resultant would look like. So I hope with this diagram you can see the perspective here. So point B is lying in the x-axis. Okay. So from point A lying in the z-axis to point B lying in the x-axis. Point C is somewhere in the xy plane. Okay. So this is in 3 dimensions. And then after we've introduced the position vectors RAB and RAC, determine their Cartesian vector form, find their magnitude, and then use them to derive the Cartesian vector form of FAB and FAC. Okay, so that's the process. Express FAB and FAC as the vector sum in Cartesian vector form of FR. So after we find the Cartesian vector form of FAB and FAC, we need to add them and introduce the unit vector for the direction of FR. Okay, so now let's solve this problem. So we write our given as such. So here FAC would have the magnitude of 120 newtons and FAB is 100 newtons. So this is our FR that we didn't know yet. So what is required here is the Cartesian vector form of FR. The resultant force. So in 2 dimensions this would be very easy, but this time this is in 3 dimensions, so we need to apply all what we have learned so far in operations in 3D Cartesian vectors. So it is said in our discussion of our approach earlier that we need to establish the position vectors RAB and RAC. So the dimensions are not here. Let me look back. Okay, so here we have the dimensions. So this should be part of your given also. We have 4 meters. We have 4 meters here and 2 meters. So let me draw that here. So this would be 2 meters. This is 4 meters. And this height is also 4 meters. Correct? Okay, so you should be able to draw this diagram for your given in order for me to understand or to see that you understand the problem when you're solving your problem sets and your quizzes. Okay, so having that, let's solve first for RAB. So R from A to B. So the easy way is to put the origin in A. Alright, so this is our origin. So what is RAB? So since A is 0, 0, 0, we will just be looking for the coordinates of B. And B is, it's 4 meters in the x direction, right? Positive x. What about in the y? There is no y component for the point B, right? Since it's lying in the x-axis alone. And it is negative 4 in the z-axis, right? So in this case, we have 4i. And we have 0j since we don't have a y component for RAB. Take note, we're just looking for RAB here. And we have negative 4 in the z-axis. That's 4k. So RAB is negative 4I, negative 4K, and that would be in meters. So RAC, let's take RAC. Again, our origin is in A, so that's 0, 0, 0. So that's just head minus tail. So our head this time is C. So point C, how can you go to point C? You need to go 4 meters in X, right? That's this one. You need to go 2 meters in Y, so you have 2 plus 2Y. 2J, I'm sorry. And still negative 4 in the K direction. So we write it down as 4I plus 2J negative 4K. So I hope at this point you don't have any problems writing down the Cartesian vector form for this position vectors. Okay, so let's find the magnitude for each one. So since these are just two components, this would be the square this would be the square root of 4 squared and plus negative 4 squared. So as you can notice, we are doing it simultaneously for both force AB and force AC. So this is negative 4 meters. So that would be 32, square root of 32, or approximately that's square root of 32, or 5.66. So that's 5. So for in your calculators, I will appreciate if you will use just square root of 32 for it to be exact. But I will just write it here as 5.66. Now let's go to the magnitude of RAC. RAC sums of the squares of 4 squared plus 2 squared plus negative 4 meters. Alright, so this would be square root of 36. So square root of 36 is 6. This is 16 plus 16, 32 plus 4, that's 6. 36. Okay, now that we have the Cartesian vector form and the magnitudes, we can find the unit vectors. So the unit vector for UAV would be the vector RAB where the magnitude are AB. So let me just emphasize that this is a vector over a magnitude. So that would be 4 over 5.66i minus 4 over 5.66k, and that is unitless. Okay, so let me write that in. So this is our minus 4 over 5 point. Again, I'm just writing 5.66 here, but please in your calculator use square root of 32 so you get the exact answer. So for UAC, this is 4 over 6, or that would be 2/3. We're just simplifying, okay? 4 over 6, that's 2/3. This is 2 over 6, that's plus 1/3. And we have negative 4 over 6, that's still negative 2/3. IJK. Doesn't look like a J. So remember, these are unit vectors, magnitude 1, but unitless. Okay, now that we have established both of that, we can write now the Cartesian vector form for our forces. So we have FAB and FAC. So for FAB, the vector FAB let me block that one. So FAB would just be equal to the magnitude of FAB multiplied by this unit vector UAB. So remember, this is a vector, so we need to block it. Okay, so the unit vector multiplied by the magnitude of FAB, which we know is 100 newtons. So this would be 100 newtons multiplied by our unit vector here for I minus the same 4 over so again we don't have a J direction here, only I and K. So for this one, this would be 400 divided by square root of 32. That would be, let me write it here, F AB that would be 400 over square root of 32, 50 square root of, that would be 70, approximately 70.71 I, and the same thing, so minus 70, they're the same values, so most probably you don't have to do that again in your calculator. And don't forget the unit, newtons. So if you check that, the magnitude should be 100 newtons. Now let's go to force AC. So again, we are doing this in order for us to get the Cartesian vector form of the resultant readily, since we derived the Cartesian vector form for FAB and FAC, and we will add them later. So I don't, okay, I will write it here for the sake of being consistent. This is magnitude FAC given as 120 newtons multiplied by the unit vector in unit vector from A to C. Okay, so that would equal 120 multiplied by this, all of this. So 120 is divisible by 3, so that would be 40 times 2, and do the other maths. Let me write it here. So that's 2/3 1/3 minus 2/3. Okay, so that's 40 times 2, that would be F AC that's 40 times 2, 80 I 40 times 1, that's 40 J, and that's again 80, since it's the same, 2/3 80K. And that is in newtons. Now, since to find FR, we need to add this too. So we need to add the components. So for this, I will use another continuation of our solution. So FR is just equal to the vector sum of FAC. Okay, let's take AB first, plus AC. And we know that you can just add all the components going in the same direction. So FR for the X components, that would be 80 plus 70.71, that would be 150.71 in the I direction. For the J direction, we don't have a Y component for FAB, but in FAC we have plus 40. So we write it down as plus 40J. I hope you can follow. I'm just adding the components here. Okay? So all that is in I, just add them. All that is in J, just add. And same goes for the K direction. So the K direction for both is, so again, I'm just adding this 70.71 plus 80 for the I, 0 plus 40 for the J, and negative 70.76 and negative 80 for the K direction. So that would just be, that would be negative, same thing, 150.71 in the K direction. That is in newtons. So this is now the Cartesian vector form of our resultant force. And to find the magnitude of that, we just need to add the squares and take the square root. So the square root of all of this, 150 so please just follow, this is taking long. Okay, square root of the sums of the squares. So we can solve FR as, so we are looking for the magnitude so that we can also determine the unit vector as well as the coordinate direction angles. So let me do that here. So that would be 18 plus the square root of, let me just input that in the calculator. Okay. So I got here approximately 216.86 newtons. So we can write therefore the unit vector for the resultant, let's call it UR, as the vector FR divided by its magnitude. So in this case, we can write it as 150.71 all over 216.86. I know this is a lot, when you are going to import it in your calculator, but it is what it is. So plus 40 over 216.86 minus the same thing, 150.71 over 216.86. So this would be IJK. And this is unitless. So for that, since this is our unit vector, we can find the corresponding direction angles by taking the arc cosine of each of this. So for alpha, for the alpha angle, that would be arc cosine 150.71 divided by 216.86. That is positive. Okay, so that's 0.69. And that would give us 45 degrees. So 45.98, or you can say 46 degrees. So let's write it as 46 degrees. So for the beta angle, you have arc cosine of arc cosine of 40 divided by 216.86. That's 0.18. And that's approximately 79.37 degrees. And for the gamma angle, it's the same as this one, but it is negative. Okay, so that's our cosine of this, negative 0.69. So the sign here is very important, because the sign determines if it's more than 90 or less than 90. So in this case, that's approximately 134.02 degrees. Okay, so the problem is only asking us about this one, this here, but it's also good to practice how to get the unit vector, u, and the coordinate direction angles. So this would be our answer. For this problem. So our next topic would be about the dot product operation. This is a vector operation that we can use to find the projection of a vector into another axis, and to also find the angle between two vectors. Again, our chapter objective. So this time, this is to introduce the dot product in order to use it to find angle between two vectors and projection of one vector onto another. So the dot product is defined as the product of the magnitudes of two vectors and the cosine of the angle between their tails. Okay, so if you have vectors A, B arranged in such a manner where there is an angle theta between them, the operation dot product of A dot b. Okay, so please be very careful in reading these operations. I know you are used to a dot b as a times b, but this time it is a dot product operation. Okay, and a dot b is equal to ab. These are magnitudes. Okay, magnitude of a times magnitude of b multiplied by the cosine of the angle between them. Okay, so these are your two vectors. They have an angle between them, and if you are asked to take the dot product of a dot b, that would be equal to ab cosine theta. So these are some laws of operations for the dot product. By the way, dot product is also known as the scalar product of vectors. So it means that you are operating on vectors, but the answer is a scalar. Okay? So it's just a magnitude, as evident here. AB cosine theta. So laws of operation, we have the commutative law. A dot B is also equal to B dot A. So it's interchangeable. Whatever the comes first, the result is the same. AB cosine theta. Number 2, multiplication by a scalar. So A times small a times A here dot B is also equivalent to our vector A dot the scalar times B. Okay, again, it's interchangeable. We also have distributive law. So if you have two vectors that you want to find the vector sum, that's B plus D, that's A dot B plus D, you just have to distribute that. That's equal to A dot B plus A dot D, or that would be AB cosine theta plus AD cosine cosine theta between A and D. Okay, so here are some laws of operation that you need to remember when operating on vectors with dot product. Now let's go to how do we formulate the dot product, Cartesian vector formulation of this. So let's analyze. If we will take the dot product of two vectors in the I direction, that is, they are coinciding or in the same direction, they will have an angle 0 between them, right? So that would be, these are both unit vectors, so they have a magnitude of 1. So that would be 1 times 1 cosine of the angle between them, which is 0. Cosine 0 is equivalent to 1. So if we need to do a dot product between two unit vectors that is in the same direction, the dot product will just be equal to 1. Okay? Let's take I dot j. I is in the x, j is in the y. So it means they are perpendicular. So if you have two perpendicular vectors, the angle between them is 90 degrees, and you take the dot product of that. So I dot j, that would be 1 times 1 cosine 90. Cosine 90 is equivalent to 0. Okay? So if you take the dot product of two unit vectors that are perpendicular, that would just be equal to 0. Okay, so now let's operate on this. Let's take A dot B, both their Cartesian vector forms. We have AX I plus AYJ plus AZK dot BX I plus BYJ plus BZK, and we perform the operation. So we have AX BX I dot I plus AX BY I dot J plus AX BZ I dot K plus you can just read through all of this, and this is just distributing, multiplying them by distribution. Okay, so we established here earlier that when you take the dot product of two unit vectors in the same direction, that would be equal to 1. If they are perpendicular, that would be equal to 0. Same goes for I dot k. since x and the z direction is also perpendicular to each other, that would be 0. So if you take all of those here, the I dot j, I dot k, j dot I, j dot k, k dot j, k dot I, all of this as 0, will only leave I dot I that is equivalent to 1, j dot j also 1, k dot k equivalent to 1. So our dot product equation would also be equal to axbx plus ayby plus azbz. So let's go back there. This is axbx times 1, ayby times 1, azbz times 1. So the rest are multiplied by 0. That's why they become 0. So we are left with the equation for the dot product as a dot b is equal to, just take all the components and multiply them. So ax bx plus ay by plus az bj. Take note, this is a scalar product. That's why you don't have ijk here. Don't be confused. Okay, so that is the formulation of our dot product. So here are the applications as mentioned before. We can find the angle between the two vectors. Since a dot b is equal to ab cosine theta, we can find theta by just transposing a dot b divided by ab, and then take the arc cosine of that. You can find the angle between the two vectors ab. And we can also take or find the components of vector parallel and perpendicular to a line. So this is the application for components. Vector, components of a vector parallel and perpendicular to a line. So here we have vector a here, and we take these are basically rectangular components, but they want to take it as parallel to a. If we have a vector a here and we have a line AA, and we wish to take the projection of this, or basically the rectangular component of this vector a along line AA, we can just take, we have a sub a, this is parallel to this one, to the line AA. So that's a cosine theta in the direction of AA with the unit vector u sub a. Okay? And we have a component perpendicular to that. So the projection of A onto the line AA, that would be a sub A is just equal to a cosine theta equals a dot product of the u sub A, or the unit vector in A. So since this is a unit vector, this is just 1. So 1 times a cosine theta. So this is basically just rectangular components. Alright. Now let's have a sample problem how we can apply this dot product operation. So we have the frame here subjected to horizontal force F. So the horizontal force is only along the y axis because it has the Cartesian vector form 300 newtons. So determine the magnitudes of the components of this force parallel and perpendicular to member AB. So member AB is this, from the origin A and then to point B where the force is applied. So what we are looking for actually is this. So we're looking for the components parallel and perpendicular. So if you can see here, this is our force directed along the positive y axis, and we are asked what is the components perpendicular, this one, F sub this, perpendicular, and F sub AB, which is acting along the line AB. So we can determine unit vector AB to find the sense of this vector. So we know that we can apply the position vector here and find this U sub B or U AB. So let's see the measurements. We have 2, 3, and 6. Okay, so from here, the measurements are, this is our given. So this distance is 6. This height is 3. And this distance is 2 meters. Is that correct? Did we interchange anything? Oh, sorry. 2 meters. 2 meters is only until here. Okay, that's 2 meters. So what we want to solve for is FAB and F perpendicular. So we will use the principle of the dot product. So why? Because we are actually asked to find the projection of force F here, the blue vector, along a line, and we can use we have here an angle theta. So if we want to find this, we can use the dot product. So required is FAB, and FAB here would be the component parallel, and F perpendicular, this symbol here. So these are what we are looking for. So what are our steps? So here we introduce the unit vector U sub B. So we need to solve for U sub B, and we will solve for that using the position vector RAB. Okay, so here are our steps. So step 1 is to draw the projection F perpendicular and F parallel or FAB, and introduce the unit vector U sub B and the position vector R sub B. And then we find FAB as the dot product of F and UB. So it means that we need to write our force F, which is given in its Cartesian vector form, and U sub B in Cartesian vector form. So that's step 3. You express U sub B in Cartesian vector form. Step 4 is to carry out the dot product operation for FAB, and step 5, express FAB in Cartesian vector form, and then determine the F perpendicular. So let's do it. So we already drawn the projection. Now we will find FAB as the dot product of F and UB. So we know here we can directly write the Cartesian vector form of our force F, right? So there's our solution for this. So Cartesian vector form of F. So this is easier, so let's do this first. So if you can see here, and even in the original problem, F is given as 300 J newtons. It means it only has a component acting along the positive y-axis. So that's 300 J. Newtons. Now what we need in order to carry out the dot product operation, for that to find FAB, we need this unit vector here, U sub B. So in order to find U sub B, we need to define AB. Okay, so what's our AB? So from the tail is from the origin A, so that would be 0, 0, 0. This means that the Cartesian vector form of our position vector will solely depend on the coordinates of B, and as you can see here, we can directly write it as this point here, point B, is in 2, right? That's 2 meters, so that's 2 in the I direction. That's 6 plus 6 in the Y direction, and another plus 3 in the K direction. So we can write this Cartesian vector form here. So 2I 6J plus 6J plus 3K. So that's all in the positive axis using the right-handed coordinate system. RAB, that would be in meters. So never forget the units. So we can find, next to find is to the magnitude. And that is just the sum of the squares of the components. So that's 2 squared plus 6 squared plus 3 squared. So that's 436, 49. And the square root of 49 is 7. I will not, let's just do this here. So that's square root of 49 meter squared. That's the magnitude. That is equal to 7 meters. So we can find now this U sub B or UAB as the vector divided by the magnitude. So we write it as RAB divided by the magnitude. So let's operate here on fractions so that we can get exact values. So I will write it down as 2 over 7 plus 6 over 7 plus 3 over 7, and that would be IJK, unit vector. unitless and has a magnitude of 1. Now that we find this, we can use this to carry out the dot product. So what we need is our f, our vector here, the blue one, dot UAB. So that's why we derive the Cartesian vector form of each. So if you can remember, the dot product would be the scalar product of these two vectors, which is we just multiply the components that goes in the same direction. That's ax bx plus ay by plus az bz. So in this case, you can see here that the components for the I and k for our f is just 0. It means you multiply 0 by 2/7 here. That would be 0. And then you multiply 0 by 3/7. That will also be 0. So it just means that our the magnitude of FAB, we can get it from here. It will just depend on the J components. That's 300 times 6/7. So 300 times 6 by 7. That's 257.14 approximately. So let me just write it here. So 0 times 2/7. So the 0 came from here because there is no I component or X component, plus that will be 300 times 6/7. And lastly, another 0. So that's 0 by 3/7. So remember, this is a scalar product of vectors. It means you're operating on vectors, but your result is a scalar. Let me write it here. So this is equal to the magnitude of FAB. So therefore, FAB is approximately 257. That is the magnitude, but we need the Cartesian vector form. So that's 257.14, and that would be in newtons, since this is this force has units of Newton, and this is unitless. The unit vector is unitless. So we have this magnitude. What are we going to do? Let me continue here. So what we need to do is to use UAB. Since UAB has the same sense as FAB, we can find the Cartesian vector form of FAB by multiplying the magnitude with the unit vector. So that's FAB by the unit vector UAB. Which means we multiply 257.14 newtons. We multiply that with 2/7 plus 6/7 plus 3/7. then we can get the Cartesian vector form of this. So using our calculators, that would be times 2 divided by 7. This is equal to, let me use a different color. The I component would be 73.47. That's I plus 220 point 41 and plus, so I'm just multiplying. Okay, so 257.14 times 2 over 7 times 6 over 7 and then times 3 divided by 7. That's 110.2. So this is I, J, and K. And this is in newtons. Okay, so I hope you follow. We did the dot product and then we defined the Cartesian vector form of FAB. We found the magnitude by the dot product and we found the Cartesian vector form by multiplying it with the unit vector that we introduced, UB or UAB. Now that we know this this unit vector here, this force vector FAB, we can simply find the perpendicular component by let's continue here, simply doing Pythagorean Theorem. Alright, since we are looking for this, we already found this. We already found F, which is in this case the hypotenuse, and we are looking for the perpendicular. So using Pythagorean theorem, we can write that F squared would just be equal to FAB squared minus F perpendicular squared. This means that F perpendicular is equal to the square root of you need to take the difference of F squared, FAB squared, this is plus, so that's F squared minus FAB squared, or the square root of 300 newtons squared minus 257.14 newtons squared. So therefore F perpendicular would be equal to 154.52 newtons. Now we have the magnitude, but we need the Cartesian form for this. And how are we going to do that? We'll still operate on vector addition. So by vector addition, we know that FAB plus F perpendicular is equal to the resultant, which is F. So it means that we can find the Cartesian vector form of F perpendicular by doing the operation F minus F AB, and we both have the Cartesian vector forms of each of these two. So F is 300G only. That's minus, let me copy that. This is 73.47 and 220.41. Plus 220.41, 110.2. That would be also in newtons. This is I. J and K. Okay, so here the component for F is 0, so that's 0 minus 73.47. So that's negative 73.47. This is 300 minus 220.41. That's 79.59. And that's 0 minus 110. That's minus 110.2. So this here now is the Cartesian vector form for our force perpendicular. Okay, do you follow? This is in Newton. So this is F. Bar. F perpendicular, sorry. So the magnitude is, we found the magnitude and also the Cartesian vector form. So the magnitude, this is the Cartesian vector form. And of course, we will compile our answers. So we have the magnitudes FAB and F perpendicular, as well as the Cartesian vector forms of each. Now let's proceed to another sample problem. So we have a pipe here, and it's subjected to the force F, which is equivalent to 80 pounds. So the task is to determine the angle between F and the pipe segment BA. So this BA, and this is the angle. So we find that angle and the projection of force F, this 80 pounds, along this segment. It means we need to find F, B to A. So as you can notice here, we have a magnitude F. We need to do dot product, so we need the Cartesian vector form of that, which means we need to define this position vector from B to C. And we also need to find the unit vector from B to A, which means we also need to find the position vector from B to A. So notice that the tail of both our position vectors would be at B. B going to C and B going to A. So our steps to tackle this problem is: step 1, to establish position vectors RBA, this is from B to A, and RBC. So we have the dimensions here, so we will do that later. The next step is to determine the angle between their tails by the dot product. So we will just manipulate the equation for dot product. That would be A dot B is equal to AB cosine theta, and we will solve for theta. Step 3, formulate unit vectors UBA and UBC. So since we in step 1 we established RBA and RBC, we find the Cartesian vector form in the magnitude, we can also find unit vectors UBA and UBC. And step 4 is carry out dot product operation to find FBA, and you can do that by taking the dot product of force F, which we already have a Cartesian vector form in step 3, and UBA, which we will find in step 3 as well. So just to visualize it, this is what we are looking for. So we have here a component perpendicular and a component parallel to the to the line BA, but we are just looking for FBA and the theta angle here. Okay, so let's go to solving this problem. Okay, so this is our givens in the problem. So the original given is this one here in the middle. We have these dimensions. We can pinpoint the location of point A, point B, and point C. So this is what we are looking for here. This is our vector. F is equal to 80 pounds, and this is what we're looking for, the theta angle and the projection of it along BA or FBA. So what is required? The magnitude of FBA, which we can acquire doing the dot product of F dot UBA, which we will derive later, and the angle theta between F and FBA. So what's our solution? So the first step is again to establish the position vectors RBA and RBC. So before we do that, we need to pinpoint the location of each point. So point A will have the coordinates this is point A. It's lying in the y-axis. So it means the coordinate in x is 0. That's comma 1, comma, this is 1 feet. So comma 1 and comma 0. So for point B, how can we locate point B with respect to the origin here? So point B is 2 feet in the x-axis, comma, that's 1 plus 2 feet in the y-axis, so that's 3, comma, you go 1 feet down, so that's negative 1 z. So this is x comma y comma z. Point C is just lying along the x-axis, so it means it has 2, this one. So 2 comma 0 comma 0 as well. So what we want to find is RBA and RBC. So if you can remember, so from B to A, it means you will subtract, that would be A minus B. For BC, that would be C minus B. So let's start first with RBA. RBA therefore will have the components, so BA, it means A minus B, if you can remember. So the head minus the tail. So 0 minus 2, that would be negative 2. That's 1 minus 3, that would be also negative 2. And that would be 0 minus 1, or that's positive 1. So the Cartesian form of RBA is negative 2y, negative 2j, and positive 1k. That is in feet. So we can readily solve for the what do you call this, the magnitude of this vector. So that's negative 2 squared, that's 4, plus negative 2 squared, that's another 4, plus 1 squared, it means 9. So the magnitude of RBA is square root of 9, or 3. Okay, so 3 this is the magnitude of BA, or the length of BA. Now let's go to our BC. So since C is the head, as you can see here in this first diagram, that would be C minus B. So let's use a different color. So C minus B, that would be 2 minus 2, that would be 0. So it means it has no component in the I direction. Then C is 0 minus 3, so that's negative 3j. And then C, that's 0 minus negative 1, or plus 1. So the Cartesian vector form for RBC is just 2 components, j and k. Negative 3j plus 1k. That is also in feet. So for this one, it would be negative 3 squared, that's 9, plus 1. That's 10. So the magnitude of this is, to be exact, let's just write it as the square root of 10 feet. So now we both have the Cartesian vector form and the magnitudes. So in order to find the angle between these two, as you can see, this is RBA and RBC. This same angle here, this is the same angle. Okay, so using the dot product, so if you can recall, our equation for dot product is A dot B so we'll just manipulate this equation, is equal to AB, that's the magnitudes, and the cosine of the angle. So we can solve for the cosine of the angle here. So it means we take the dot product A dot B divided by the magnitude AB, and we take the arc cosine of that, and we will find this angle. So rewriting using our, so the theta angle would just be equal to arc cosine of, in this case, that's RBA dot RBC divided by the product of their magnitudes. Right? So RBA times RBC. So let me continue this on another page. So here RBA dot RBC would just be equal to, that would be AXBX plus AYBY plus AZBZ. So since we only have two components for RBC, we can write that down as, that's no component for, so that's negative 2 times 0. Next is plus another negative 2 times 1 plus 1 times 1. All over 3, the magnitudes, 3 feet so this will have feet squared as well. The units, square root of 10 feet. So we can solve the angle. This is by the way arc cosine of that. Okay, so this is, we need to take the arc cosine of this. Okay, let me write it here, cosine negative 1. So solving this, that would be, oh I'm sorry, this is not negative, this is not negative 2 times 1, this is negative 2 times negative 3. So that's a positive value. So that's 6 negative 2 times negative 3, 6 plus 1 times 1, that's 1 divided by 3 divided by square root of 10. So the answer is approximately 0.7378, and we get the our cosine of that. We get 42. So we already answered the angle. So we have 42 using the dot product. 45 degrees. Okay, so now that we have the angle, we proceed to finding FBA, or the projection of our force 80 pounds into segment BA, and we will do that by doing another dot product. So continuing, we can use RBC, which is negative 3J plus 1K. So that's negative 3 plus 1 J. This is J and K. This is our this is our BC. And the magnitude is square root of 10. It means that if we take our BC here, which the value is square root of 10, and we multiply that with, since we are looking for, you can see here, we are looking for the Cartesian vector form F, which happens to be on the same line as our BC. That's why we can find the unit vector UBC and multiply it by 80 pounds, and we will get the Cartesian vector form of our force 80 pounds. So let us just go direct here and multiply this by 80 pounds. So the Cartesian form of our force F would now be, so we are getting the Cartesian form of this to perform the dot product operation afterwards. So we have 80 by 3 divided by square root of 10. The answer is 75.89. That's J, since we don't have an I component, plus 80 over square root of 10. That's 25.3 K. So 25.3 K. This is the Cartesian vector form for this in pounds. So what do we need next is okay, let me just write here quickly. This is F times U BC. So UBC is just equal to RBC over the magnitude of BC, which is square root of 10 feet. Now we are going to solve for let me write it here. So you have UBC. Here we are looking for UBA. And UBA is just equal to RBA, which we have the Cartesian form of, divided by its magnitude. So let's take a look. That would be -2, -2, and 1. So we can write it here as -2 over 3, -2 over 3, and positive 1 over 3. So that would be the Cartesian vector form of UBA. We need it to find the projection of F along the line BA. So after this, we will just do the dot product. And this is, by the way, unitless. Okay, so now, to find the magnitude of FBE, the scalar product of vectors, we need the dot product of F dot UBA. So that this dot product operation will give us the magnitude FBA, which is what we are looking for. So again, that would be AXBX plus AYBY plus AZBZ. So in this case, let me write down everything. So we have 0, we have 75.89, and we also have 25.3. That is for the Cartesian form of F. For the Cartesian form of UBA, that would be 0 times -2/3. This would be 75.89 times -2/3, and that would be 25.3 and divided by 1/3. So this here are plus operations. Therefore, FBA would be equal to, this is 0, this is 75.89 by -2 divided by 3. That's a negative value. And 25.3 divided by 3. Let me correct this. So this is -3 by 80 divided by square root of 10. So this should be a negative number. So this is -75, and this is -75.89. So it means this is negative. So this is positive, and this is positive. So we add them. So 75.89 by 2 divided by 3 plus 25.3 divided by 3. So our answer is approximately 59.0 pounds. So we compile our answers here. So answers, we are only looking for 2. So that's the projection FBA and the angle. So FBA, we solved it as 59.03 pounds, and the angle is 42.45. Angle 42.45 degrees. Never forget your units. So now we solve this problem by following this steps and approach using the dot product operation. So as always, thank you for your attention, and this part of our lesson can be found in our reference book, Engineering Mechanics Statics by Russell Hibbeler, and this is still in chapter 2, the last topic, pages 56 to 73. So thank you.